We will start with our first speaker, which is Yuan Li, which is from University of Liverpool. And Yuan, if you would like to go ahead and share your slides, we will begin with your webinar.
Hello, everyone. Thanks AI for giving me this opportunity to deliver a talk on the high-throughput robotic colourimetric titration by using computer vision. My name is Yuan. I'm currently a final year PhD student in Cooper Group at the University of Liverpool. And my work is on the high-throughput materials discovery for the hydrogen peroxide photoproduction. In my work, chem speed was used for dispensing solid and liquid, and then a 48-well platform was developed for the light irradiation, but for the hydrogen peroxide quantifications, only a traditional UVS spectrometer was used. And here is the audiometric method illustrations. As we can see, this method is really time-consuming, and the detection limit for it is just micromole per liters. So dilution is always required for the most samples. So based on this, it is not adaptable for the high-throughput materials discovery for the hydrogen peroxide photoproduction. So it's urgent to solve this problem, but let's first see the recent progress of the high-throughput technique in chemistry. And here is a workflow for the candium selenide nanocrystals synthesis. In this workflow, a commercial liquid handling robot, Opentrons, was used for the simple preparations. And some other groups, like the Basford, has developed a workflow for the porous organic cages screening. In their workflows, the Opentrons was used for the distribution of the monomer solutions. And very recently, due to the advances in the computer visions, some groups has tried to combine this with the high-throughput screening. For example, Microsoft in these examples was integrated with the Opentrons to achieve the in situ analysis of the active body labeling. And also some groups has used the digital camera to monitor the work up procedures during the organic synthesis. And very recently, in this kinetic color works, it has used the digital camera to monitor the reaction progress. So based on this, we are thinking if we could combine the Opentrons and the computer vision to achieve the high throughput hydrogen peroxide determinations. So in my firstly, we investigated the existing hydrogen peroxide determination method, and we found the chemical titration between the potassium permanganate and the hydrogen peroxide is the most suitable method for the hydrogen peroxide determinations, and this method possessing a color change from transparent to the pale pink at the endpoint. So for the liquid handling, we try to use the Opentrons to handle it. And for this color change, we select the CIELab color models, which possessing the A-star channels corresponds to the green to red color changes. And to achieve the in situ color analysis during the titrations, a digital camera was attached to the pipette mount, and for the information transfer between the computer and the Opentrons, service message block server was built, and all these lampware and liquid transfer rules was defined into configs and then controlled by the hydrogen peroxide protocol master through the control of the hydrogen peroxide protocols. And now let's see the development of this protocol. This is the layout of these titration workstations, and except for the camera position at deck 3 and the plates at the deck 5, all other lampware's position is interchangeable. But we still have one problem haven't been fixed, is how a robot select a suitable potassium permanganate for the titrations. So to solve this problem, in our case, we try to separate the hydrogen peroxide into 4 different ranges corresponds to 4 different concentrations of the potassium permanganate. And after adding the certain volume of the potassium permanganate, the first well with A star value higher than 0 will be selected. And this stage was called the pre-estimation. And following this, the layout of the plate and deck file was separated into parts. The first 4 rows will be used for the titration to avoid the random error, and the last 4 rows will be used for the pre-estimation. And here, this is the schematic representations of this whole workflow, including the process, image capture, and the signal processing. And except different from the traditional titration chemistry, only one pre-estimation stage was created to make sure the continuous automation. And after these workflows, we could gain the consumed volume of the potassium permanganate and then calculated the hydrogen peroxide concentrations. And here is a video demo for this workflow. And this is the layout of this workstation. And after inputting the lamp wire and transfer rows, the robot will start at the sulfuric acid as a buffer for the chemical titrations. And then the hydrogen peroxide samples will be added to each columns, and the tips will be replaced to avoid the cross contaminations. And after completing these 2 parts of the plate preparation, a blank image was captured to achieve the confirmed area for the following color information extraction. Then the pre-estimation stage was triggered. 4 different concentrations of the potassium permanganate will be added. And one extra mixing was introduced to make sure the reagent was react thoroughly. And the reagent tips will avoid the cross contaminations among different samples. After completing the pre-estimations, a black image will be taken and to decide which is the first wells with an A star higher than 0. After this, the robot will take this information for the following titrations. And for each step of titrations, it will take an image as a record. After completing the titrations, it will start to process these signals, like the A stars versus the volumes, and then carry out the fitting analysis to gain the consumed volume of the potassium permanganate. And then this is the document storage for each batch of the run. And the code records help the chemist to know what happened during the titration workstations. And it is also important once we develop an analysis workstation to evaluate its performance. Firstly, we try to compare the CIELab color models with the UVVS, and it shows a good linear relationship. And then we try to compare its results with the aldometric method, and the relative difference is within the 95 confidence intervals. And also for the automation, the operation time is also important. 48 titrations cost 6 hours, and also this workflow is flexible. And to validate its real-world applications, we firstly apply it to monitor the hydrogen peroxide photoproductions by using the reported D7, and its results is consistent with the aldometric method, and then combined with the previous developed workstations to screen the photocatalysis, and this part of work is still ongoing. And based on the previous descriptions, it's only hydrogen peroxide, and we can see its lump sum for this workstation. So to improve it, we try to replace the CIELab models with the CLCH color models. As we can see from this graph, the hue parameters is like a nature property of different colors. And by applying this, we could achieve the acid-base titrations and complexometric titrations. So this modular design could allow us to monitor any reaction with the diagnostic color changes. And to summarize, a high-throughput robotic colourimetric titration workstation was established, and it can achieve the chemical titration endpoint analysis just within microliters of the sample volume. And interactive user-friendly interface was developed. And this workstation can not only achieve the monitoring of hydrogen peroxide photoproductions, but it can also adapt to various colourimetric titrations. So finally, thanks Professor Ed Cooper and Dr. Schauler for their work, supervisory, and Biplam, Rob, QJ for their contributions to this work, and thanks for your attention.